This is the second video on the subject of the example surface magnet, permanent magnet brushless motor. I should emphasize again that this is not a complete design project, but simply a guide to some of the magnetic and electrical parts of the design process. I would like to dedicate this presentation to the memory of Bernard Haig, who passed away nearly 60 years ago when he was the James Watt Professor of Electrical Engineering at Glasgow University. His work on the solution of the field equations in electric machines is only part of his work in electrical theory. After nearly 100 years since their original publication, we will find limitations which come into sharper focus when we compare his harmonic field solutions with modern numerical analysis. And I can only say how interesting it would be if we could share our modern methods and facilities with Haig and many other pioneering engineers from the past. As I normally do, I would like to emphasize that although these videos are generously hosted by JSOL, they do not represent JSOL in any way. Also, there is no connection with any JSOL software. The presentations are entirely about classical machine theory, and they represent a personal view. In this presentation, I'm going to make use of Chapter 4 and Chapter 5 in the Green Book, which was published almost exactly 10 years ago by Jim Hendershot and myself. If you already use the Green Book, I hope this presentation will provide a useful example. If you don't use the Green Book, I should point out that all the theory and formulas are also available elsewhere in the published literature, some of it very old, but the Green Book collects quite a lot of it together in one place. I will make reference to some of the seminal places, some of the seminal papers along the way. Our objective is to try to do the basic magnetic and electrical calculations. The process is described rather carefully from a theoretical point of view because it follows the classical theory, which is very old, some of it going back more than 100 years. The actual calculation can be quite tricky in places, even before we start using complex numbers. In the early days, engineers used slide rules and log tables, so their work could be very tedious. Today, of course, we have much better facilities for these calculations. But the classical theory hasn't changed very much. What has happened instead is that the numerical analysis methods, including the finite element method, have become so fast and so accurate that they tend to displace the classical methods completely. Modern numerical analysis copes with saturation and complicated geometry, two very important, unavoidable features of real machines that could never be handled completely satisfactorily before. Beyond that, modern numerical analysis covers many areas in mechanical engineering in equal depth, far beyond what we can do here with the classical electromagnetic machine theory by itself. However, the classical theory remains important as a means of making approximate checks on numerical analysis, and it provides insights into the working of the machine which do not always emerge automatically from the volume of results coming from numerical analysis. It also provides methods for quick estimation and sizing. From it we can expect precision in the sense of precise thinking and concept modeling, but we cannot expect very high accuracy in the sense of exact agreement with test data. In my opinion, we need both of these approaches, and of course we also need a third, which is physical testing. So let's go back and remind ourselves of the dimensions. The outside diameter is 120 millimeters, the stack length is 50 millimeters, rotor diameter is 76 millimeters, magnet length is 8 millimeters in the direction of magnetization, which is radial. We have 10 10 poles, and a 3-phase stator with 12 slots. So 12 slots and 10 poles, 1.2 slots per pole. Note the slot opening here is 3 millimeters, and the slot area is 200 square millimeters. We can also go back and have a look at the winding. You may remember we synthesized this 3-phase winding, and in that process we also calculated the winding factor at the working harmonic, 0.933. We will need the winding factor again in this section. In this winding, the number of coils is equal to the number of slots. So we have 2 coil sides per slot. Each coil is wound around 1 tooth, giving a coil span of 1 slot pitch. There are 4 coils per phase, and in each phase we can find 2 groups of coils, each group comprising 2 adjacent coils wound with opposite polarity. The spacing between the axes of adjacent coils is 30 mechanical degrees or 150 electrical degrees, since the number of pole pairs is 5. We're going to start by calculating the fundamental flux per pole, phi m1, and from it the fundamental time harmonic component of the EMF EQ1 by a very old process which goes back about 100 years. The modern implementation of it with high coercivity permanent magnets was originally described by Nady Boulez in the IEEE transactions in 1985. Boulez used a field solution which had been published by Bernard Haig of Glasgow University originally in 1926 in World Power Journal, and later in book form in 1929. We can see Haig's solution here reproduced from the Green Book. A and B define the outer and inner boundaries of the solution domain, and the iron is assumed to be infinitely permeable. It has to be said that this is a serious limitation of Haig's method, and a strong reason to use the finite element method in general, although the error in this particular example will be quite small. Many other authors have developed field solutions of this type, notably Howe and Zhu at Sheffield University. And what we're looking at is a solution of Laplace's equation in the air gap and Poisson's equation in the magnetized region of the magnet, expanded in an infinite series of harmonics, n from 1 to infinity. Note that n is the order of the mechanical harmonic, not the electrical harmonic, so it includes all harmonics and not just the electrically interesting ones. In our case, however, we are going to pick out the working harmonic, which corresponds to P equals 5 pole pairs, so n equals 5, and this is the first or fundamental electrical harmonic. In passing, we should note that the convergence of the infinite series is very slow, as Haig himself pointed out in 1926. This is not troublesome when we're calculating only the working harmonic, but it is very troublesome if we try to calculate the field distribution or the air gap component of the winding inductance. Also note that the stator bore, that is the inside surface of the stator, is taken to be a smooth cylinder, so the slotting is neglected. Some authors have actually used the method of conformal transformation to analyze the effect of slotting, but here we will simply use Carter's coefficient in the time-honored tradition of electric machine calculations. Carter's coefficient enlarges the total effective air gap slightly, and in a surface magnet motor the effect is very small because we use it with the sum of the physical air gap and the effective magnet length in the direction of magnetization. It's only about 1% in this case, so it's not a serious error to ignore it. It's interesting to note that Carter's coefficient is also based on the method of conformal transformation, a very sophisticated application of it, originally published in about 1901. Now, Haig's formula is for a pair of filamentary conductors at the radius C, carrying currents I and minus I. What Boulez did was to use Stokes' theorem to convert the volume magnetization vector of the magnet into a distribution of current on the surfaces or the edges of the magnet. For a radially magnetized magnet, the result is particularly simple, and it is shown here as K amperes per meter along the edges of the magnet. K flows, of course, in the axial direction, and it goes without saying that we're dealing with a 2D, two-dimensional field solution, infinitely long in the axial direction, the Z direction. M is the magnetization. Boulez modified this magnetization to allow for the recoil permeability of the magnet, and his adjustment, K subscript M, is typically of the order of 0.98 to 0.99. Boulez actually integrated the field solution equation with respect to R along the magnet edges, but here we are going to use 10 intervals giving 11 filaments IJ and add them all together. Here I've actually gone a little further than Haig or Boulez and further than the Green Book in using this equation in the Z component of vector potential, which is easy to calculate by integrating the radial flux density BR with respect to theta, the coordinate angle. Then I take the difference between the vector potentials spaced at one pole pitch, aligned with the center line of the magnet, and if I'm working with only the working harmonic, this gives me immediately the fundamental flux per pole phi m1 in Webers. I can use this directly in the formula for the fundamental phase EMF using this equation, which is in every textbook on AC machines, including, of course, the Green Book. This is, of course, an open circuit calculation with no current in the winding. And you can see in here I have grouped some of these expressions together with labels T, U, V, W to help in the calculation process. Here is the calculation performed in Microsoft Excel, which is adequate for the working harmonic. At 1000 RPM, revolutions per minute, we're getting a phase EMF of 15.712 volts RMS. Note the frequency, 83.333 Hertz, which is rather high for ordinary electrical steel, so we need to keep a watch on the core loss. Also note that this calculation tells us nothing whatsoever about the harmonics in the EMF waveform. So although the working harmonic is the most important one, the picture is by no means complete. The formula allows us to calculate also the fundamental space harmonic component of flux density in the air gap. It's 1.2 Tesla, which is pretty high. But that's what happens with high energy magnets, and we'll just have to be ready to use low loss steel to limit the core loss. We can see here also at the bottom right the air gap component, or the magnetizing component of the synchronous inductance, calculated by two slightly different methods. Let's have a look at this next. In fact, what we're going to do is to resolve the inductance completely into its classical components, starting with the magnetizing inductance. The so-called magnetizing inductance, LMD, is the main component of the synchronous inductance, and once again it is a very old concept. I wouldn't like to say how old, but certainly it goes back to Steinmetz in the 1890s. Recognizing that AC machines produce torque from the fundamental space harmonic components of flux and ampere conductors, it has always been of interest to know the inductance associated with the fundamental ampere conductors, in particular when all three phases are working together in a balanced condition. That's what we call the magnetizing inductance, a very old term, and it's not obvious from the name that it includes only the working space harmonic. All other components of inductance are lumped together in the leakage inductance, and the distinction between magnetizing inductance and leakage inductance is vitally important because these components affect the performance in different ways, not only in the steady state, but even more so under transient or unbalanced or fault conditions. With that introduction, the classical textbook formula for LMD is this one at the bottom. D is the diameter of the stator bore, G is the air gap length, usually modified with Carter's coefficient, P is the number of pole pairs, and KW1 is the winding factor at the fundamental electrical harmonic, the working harmonic. TPH is the number of turns in series per phase. And I would say all these items will be thoroughly familiar to any AC motor designer, whether of synchronous machines like this one or of induction motors. So if we go back, we can see the value 43.6 microhenries. Now, the narrow gap formula assumes that the flux crosses the air gap in the radial direction. And when the air gap is very small, this assumption works well, particularly in the induction motor or the IPM, where you don't have this large effective air gap through the magnet. But in the surface magnet motor, the effective air gap includes the radial length of the magnet in the direction of magnetization modified by the recoil permeability, and it's much bigger. In fact, this value is 8.62 millimeters compared with the physical air gap of only 1 millimeter. This means that the flux can spread out in the tangential direction, increasing the permeance and therefore the inductance. To calculate this, we first calculate the inductance due to the fundamental space harmonic component of the flux produced by a coil whose coil sides are filaments placed one pole pitch apart, located at the stator bore. We can see these filaments, and we can use the very definition of the winding factor, which tells us that the fundamental flux produced by the actual winding is equal to the fundamental flux produced by the concentrated coil multiplied by the winding factor. The way we use this is to assign the current KW1 T phase divided by 2p amperes in each coil side filament. And then we calculate the flux linkage using an integral of Haig's Haig's flux density formula and refer it back to 1 ampere. Hence we get the value of LMD, which if we go back we can see has a value of 56.6 microhenries, quite a bit bigger, in fact 30% bigger than the classical narrow gap formula, 30% bigger. The accuracy of both these values is questionable because of the limitations I mentioned earlier. Unfortunately, this does not affect the torque calculation, but it could affect the calculation of the terminal voltage when the machine is operating. Now, although the magnetizing inductance is part of the synchronous inductance, there is another way to calculate the synchronous inductance which works very nicely for non-salient pole machines like this one, but not quite so simply for salient pole machines like the IPM. And this is the difference between the phase self-inductance, and the phase-to-phase mutual inductance, LPH minus MPH. It's interesting to see where this formula comes from, and it's quite important because it relates the inductances to Parkes transform, that is the dq axis transform. We start down here at bottom left with the phase inductance matrix, which for a three-phase machine contains 9 inductances, 3 self-inductances on the diagonal and 6 mutual inductances on the after diagonals. You note that it's a full matrix, which means that the 3 flux linkage or voltage equations for the 3 phases are not independent. The important property in this very simple case is that the phase self-inductance and the phase-to-phase mutual inductance MPH are constant, and in particular that they are independent of the rotor position. This is very nearly the case in the surface magnet motor, and it's what we mean when we say that it is a non-salient pole machine. In the IPM, these inductances vary with rotor position and also with current, and the situation is a lot more complicated. We call the IPM a salient pole machine because its inductances depend on rotor position. Now, there isn't space here to go into all the details of Parkes transform, although we can certainly see the important features of it here. For the inductance matrix, it's a question of pre-multiplying by the inverse of this T matrix and post-multiplying by T itself. Now, T is this matrix in the middle, and theta is the rotor position, actually the angle between the d-axis of the magnetized rotor and the axis of phase A in electrical degrees in this instance of it. T is the matrix expression of Parkes transform. This is the actual one used by Park, and it can be interpreted as a mapping from the stationary coordinate system of the stator to the rotating coordinate system of the rotor, which is rotating at synchronous speed. I might mention in passing that this form of Parkes transform is not orthogonal, and in other words, it's not the transpose is not equal to the inverse. There's a coefficient of 3/2 here, but it's still perfectly okay to use it, and this is the one that is most commonly used. In wound field machines, it does lead to non-reciprocal mutual inductances in the transformed inductance matrix, but we don't need to worry about that here because we don't have a field winding. So the result of this transformation, which looks like a diagonalization transformation, the result is this matrix LDQ0, which is the inductance matrix in the synchronously rotating coordinates. And the remarkable thing is that it's diagonal. Not only have we reduced the number of inductances from 9 to 3, but we've ended up with 3 independent equations instead of 3 dependent ones. There is, of course, a corresponding transform for voltages, flux linkages, and currents, using only the T matrix with a vector of currents or flux linkages or voltages. But it turns out that if the machine has a star-connected winding, the 0 component of current is 0. So this element in the matrix becomes redundant. Also, in a symmetrical machine, like this one, the D and Q axis inductances turn out to be equal. There may in fact be a very small difference caused by the nonlinearity of the steel in the magnetic circuit, such that one axis saturates more than the other, but this effect is generally very small and will certainly be negligible here. Before we leave this slide, we should just note that the 0 component is a mathematical requirement to keep the transform matrix square, so that we retain a determinate set of 3 equations, having started with 3 equations. This principle is not spoiled by the 3-wire connection, but merely simplified in that the zero current component is 0. The 0 component is called the zero sequence component, and for fault conditions when the 3-phase currents do not sum to 0, we must include it. But we can forget about it here. Although the relationships between the synchronous inductances and the phase inductances are quite simple for the non-salient pole machine, we still have to go quite deep into the theory to determine the phase self-inductance LPH and the mutual inductance between phases MPH. And although this will appear to be quite a lengthy mathematical process, it is important because of the insight it gives into the design of the machine and how the different components are constituted. The phase self-inductance LPH is considered to be the sum of an air gap component LG, an end winding component LEND, and a slot leakage component L slot. A similar relationship holds for the mutual inductance between phases. And before we go into the analysis, let's have a look at the result. First, we can see that the end winding inductance in this machine is quite small. This is partly due to the fact that it's associated with flux around the end windings, and since the flux paths are entirely in air, the inductance is naturally low. But also in this 12-slot machine, the end windings are physically quite small, and this contributes to the low value of LEND. Similar factors apply to the end winding component of the mutual inductance, but in addition to that, the physical spacing of conductors belonging to different phases is quite large, so the resulting value of MEND is really quite small, and here we're going to ignore it. The largest component of LPH is the air gap inductance LG, but it's not very much bigger than the slot leakage inductance L slot. It's not that the slot leakage inductance is large, in fact it's not particularly large, but that LG is relatively small, and that is due to the large effective air gap through the magnet. In an IPM or an induction motor, LG would be much bigger, an order of magnitude bigger, and L slot would then seem small by comparison. We're going to calculate LG by an approximate method. We've already calculated the air gap inductance LMD, but that accounts for only the fundamental space harmonic component. The total LG includes all the space harmonic components, including any subharmonics whose pole number is less than 10. Also, where LG applies to one phase acting alone, LMD applies to all 3 phases acting together, and it's part of the classical theory that the component associated with one phase acting alone is 2/3 of this value. So here at the bottom we see the difference between LG and 2/3 of LMD, 47.8 microhenries, and this is what we call the differential leakage or the harmonic leakage inductance. It's the inductance associated with all the space harmonics produced by the phase winding except the working harmonic. A similar process finds the differential component of the mutual inductance between phases, except that here the coefficients are slightly different, as explained in the Green Book. That 2/3 factor appears in LMD as a 3/2 factor we saw before, and it is the only hint that LMD was effectively calculated in a synchronously rotating frame of reference by adding the contributions of the 3 phases with balanced 3-phase current. We never saw Parkes transformation when we were calculating LMD, but it is implicit. And this concept of magnetizing inductance goes back before Parkes transform was published in the 1920s. To calculate the air gap inductances Lg and Mg, we're going to use the connection matrix method of Gabriel Cron, which was published in 1940. We have 12 coils, and each one has a current and a flux linkage. So psi naught and I naught are vectors of dimension 12, and there is a 12 by 12 matrix L naught, which is the matrix of all the inductances between these coils, self and mutual, before any connections are made between them. The connections are defined by a connection matrix C and its transpose CT. It's easy to see how this matrix is formed. For example, the current in coil 1 is equal to IU, the current in phase U. So we put a 1 in this element at the top left. Similarly, the current in coil 2, going back to the connection diagram, is the negative of IU. And similarly for the currents I7 and I8. This way we build up a complete definition of the coil connections in 3 phases. We're using the transpose CT to define the current connections, and it's remarkable that the flux linkage connections are then automatically determined by C itself. This is not obvious, but it's an amazing property of the connection matrix. The matrix is not square because it is connecting 12 independent coils into 3 circuits, 3 phases, so its dimensions are 12 by 3. It doesn't have to be square because it is never necessary to invert it. When Cron first published this type of method, it met with quite a bit of opposition, as you can imagine. Very briefly, it follows that the inductance matrix of the connected up 3-phase circuit is obtained by pre-multiplying by C and post-multiplying by CT, and that's what we're going to do. We'll see the result in a moment, but first let me apologize for the mixed notation. Earlier we were using ABC for the 3 phases in Parkes transform, but here we're using UVW. So I apologize for that. There are in fact many different conventions, and I have made a table of typical ones here. It's rather lazy of me to change notation in the middle of a presentation, but on the other hand, when we're reading papers on this kind of subject, we do have to cope with different conventions all the time. So I would try to defend myself on that basis, but I do apologize for any confusion. Okay, so here we see the post-multiplication by CT. And although the original L0 matrix is full, because it's symmetric, I don't need to write out all the terms in the lower half. And note also that in the result over here I've used the symbol H equals L minus M, really just to make the result look a little cleaner and simpler. We don't need to stop here, but to go on to complete the matrix multiplication, and here is the result. So this is the pre-multiplication by the C matrix. And the result is this tiny inductance matrix 3 by 3 at the top right. It's rather extraordinary that this matrix is diagonal, which means that the air gap component of the mutual inductance between phases is 0. This is not the case in general. It's a peculiar property of this particular machine, and it comes from the fact that the coils are not overlapping. Each one spans 30 mechanical degrees and does not overlap the next coil or any other coil. The self-inductances are all equal to 4H, or 4 times L minus M. So now we need to calculate L and M, self-inductance of one coil and the mutual inductance between any two coils. And to calculate L and M, we consider the flux distribution produced around the air gap by one coil. It's highly idealized, of course, but it's simple and reliable, and it can be found in every serious textbook that deals with electric machine windings. We have two coils at theta 1 and theta 2, and the flux distribution in the air gap is rectangular, as shown. By applying Gauss's law and Ampere's law, we can calculate the flux densities inside the span of the coil and outside, and then by integrating in the tangential direction we can get these expressions for the self and mutual inductance of the coils. And from this we get Lg, which is equal to 85.5 microhenries per phase, and as we said earlier, Mg equals 0. Next we have to calculate the slot leakage inductance. This is a very common standard calculation in which we use the slot permeance coefficient and the number of or the square of the number of conductors in each slot. Again, we can find this formulation in every serious textbook on electric machines. The slot permeance coefficient depends on the position of the current of the conductors in the slot. And here we've taken an average between the top and the bottom of the slot. So the result is 78.6 microhenries per phase for L slot and minus 13.3 microhenries per phase for M slot. Finally, the end winding inductance is calculating using this simple formula, which comes from the famous book by Grover published in 1949. Actually, the theory of this goes all the way back to James Clerk Maxwell, and it was discussed extensively by Rosa and Grover of the United States Bureau of Standards, who published a large number of inductance formulas between 1910 and 1920. You can find this very easily on the internet. It's still available. While we're here, we can still see a representation, a simple representation of the shape of the end winding, from which it is possible to calculate the mean length of one turn, and then from that and the wire size we can calculate the phase resistance, which comes out 46.8 milliohms per phase. Now the wire size is deduced from a consideration of the slot fill factor, and the drawing shows a possible arrangement of conductors which gives a slot fill factor of 34% with a wire diameter of 1.9 millimeters. That is quite thick wire, rather stiff, and we might want to divide it into a number of smaller strands, but I won't pursue that here. We can now collect all the inductance parameters together, and here they are in the table at the bottom left. The values are given in millihenries per phase and also in per unit, using a base impedance calculated from the current and the EMF, which is the quotient of which is an impedance. Since we have a wire diameter, we can estimate the current if we assume a current density, and I'm going to use a rather high value of 12 amps per square millimeter, which is very high for a small totally enclosed motor with no special cooling, although it might be acceptable for intermittent operation. The resulting current is 34 amperes RMS, and if we multiply this by the generated EMF and the number of phases and divide by the angular velocity at 1000 RPM, we get the electromagnetic torque, which is 15.3 Newton meters. The power is 1.6 kilowatts, and the torque per unit rotor volume comes out to be 67.5 kilonewton meters per cubic meter, or newton meters per liter. This is a very high value for such a small motor, although it is feasible to consider it for short-term loading, intermittent operation. Note also that the copper loss is also included here, 162 watts. I might mention once again, the per unit values are useful in assessing really the relative magnitudes of the voltage drop produced in each one of these inductance components. So here it is in per unit and also again in percentage. We've said that this motor might be running hot. Let's see a little more detail. All we've done is to work with a current density, a high current density of 12 amps per square millimeter, and although we have also noted that the core losses may be high as well, we haven't actually calculated them. So what we're looking at here may be somewhat optimistic. The overall size of the stator is something like this cylinder, which has a surface area of about 37,700 square millimeters. To dissipate 162 watts of copper loss alone, we need a heat transfer rate of about 4,300 watts per square meter. Now, natural convection gives a rate of something like 6 watts per square meter per degree C at best, and at that rate the surface temperature would be 716 degrees C. Clearly that's not practical. To limit the surface temperature to 60 degrees C, let's say, we would need a heat transfer coefficient of about 72 watts per square meter per degree C. This might be feasible with forced cooling, possibly water jacket cooling or very strong fan cooling, but of course it's only the surface temperature, what is going on inside. Here I'm afraid I'm going to leave the question open because it's much too complicated to answer by simple calculations. What is needed, obviously, is a detailed thermal analysis, and that is more complicated than the electromagnetic estimation that we've been doing. So really, all I'm doing is using this example to emphasize the importance of thermal modeling. Lastly, here is a list of the things that we haven't calculated. There's a lot of work to do, and in this short video we have only scratched the surface with a very rough estimate of the electric and magnetic sizing. When we look at this list, we can see in perspective how small a part of the overall design and manufacturing process is the electromagnetic estimation that we've covered here. Of course, it's essential, and it's quite specialized and even complicated to understand, but it remains only one small facet of the whole process. Thanks for listening.